requirements, surface water system assessments, total maximum daily loads. This is an engineer. Relicensing of hydropower facilities and water quality management for multiple uses, such as supply, recreation, and other uses. He has additional experience developing water quality monitoring plans and conducting field work. Dr. Annear has also conducted numerous peer reviews of surface water models for agencies such as government departments and academic institutions. He has conducted research and projects in areas ranging from river and temperature modeling, riverine heat budgets, steam bed heating, turbidity modeling, mixing zone analyses, and permitting analyses. He also serves as a reviewer for various water resource and hydrologic journals and has served on the EPA National Water Quality Grant Reviewing Panels.
Good afternoon. So what I thought I'd do today is talk to you a little bit about background about who I am as a user, and then talk a little bit about the various uses of the data. And one little story that I can compare to is I was once asked to review a publication for an international journal to do with how you model with computers solar radiation. And I opened it up, and the first 12 pages was my paper from 3 years earlier. So the review was easy. Within 10 minutes of me submitting my comments, it's one of those push-pull technology things with AGU and Water Resources Research Journal that immediately went out within 10 minutes. The publication was no longer up for review. Everyone could stop what they were doing. It was withdrawn, obviously. So the company that I worked for, DHI, originally started back in the 1960s as a research institute, sort of a branch of the Danish government. And over the years, the decades, two things sort of developed. One, government funding went to zero, and two, they basically expanded and took advantage of technologies that became available and started developing computer models that could help them. Previously, they've been using simply physical models, large warehouses with 1/3 scale or 1/64 scale systems. Basically, DHI's sort of mantra for being is basically modeling the world of water, helping people solve problems. And that's very data intensive. We tend to work in three large areas. Basically, your surface water, freshwater systems, your coastal marine, and then your urban infrastructure. Think of sanitary systems, water distribution, the pipes, etc. So we have globally, we have offices in 26 countries and 1,000 staff, and the majority of those are geeks like myself. So to kind of break it down, again, this is just background to give you context. So we basically do specialized consultancy. Some of us would think of this as the hired gun, but we're a little bit different animal. We don't have to make a profit. We have no shareholders. We have no fat cats. So we really are an institute in many ways. But we do consulting work, and we compete against all the big firms that are out there. But we stick to just water. Some of our clients, some of the same folks we talked about today, who I'll show you later on another slide, who we get data from. We're often asked to work with local communities, state agencies, the federal government, but also private entities. So we're often hired to help people solve problems. And that could be advising them on data collection, it could be them using data. We also work with nonprofits. So the kind of data. So now you're getting into modeling and what that means. How is data needed, used, applied in the private sector? So oftentimes out there in the world, you have to do these periodic studies and evaluations. Maybe you're a city or municipality, maybe you're a company. You have to update your facilities to handle stormwater or to handle sanitary systems. And you need to do a review. So you might be collecting data to meet environmental requirements that change over time and upgrade that infrastructure. Sometimes you're trying to identify new sources of water and feasibility. It might result in new water rights, maybe not. New infrastructure and upgrades. So this could be everything from Department of Transportation wanting to put a new bridge in, to a city, county wanting to refurbish some piece of infrastructure that impacts the water. Could also be the federal government wanting to put new facilities at say a port terminal for the military or something like this. But also water rights has become a big issue of understanding. There are folks out in Idaho, Washington State who are starting to look at this exact issue you have in Colorado, looking at groundwater impacts on surface water rights. And people are saying, well, rather than go to court, can we find a way to solve this? And then one of the more recent occurrences with using data has been ongoing operations. Folks have said we're tired of these periodic studies. We want to use data to help us better manage our resources every day. And so this could be anything from a water distribution system or a sanitary system. It could be stormwater control. You're trying to make sure you're in compliance with EPA regulations. It could be hydropower operations. A lot of hydropower facilities in the West are also responsible for flood control. So can you maximize hydropower while still storing enough water or leaving enough space in your reservoirs for flood conditions? So those are big challenges out here in the West. In addition, there's this idea of better use of the water. So you hear all kinds of things about conservation in cities and counties, but then what about the irrigation districts? They realized long ago about water conservation. Now they're seeing the light of some of these new technologies where they can get real-time data being sent to them to some type of interface that allows them to manage better. What we call more efficient or on-time delivery. But also flood control. People are starting to look at, I don't want to just know when the big one comes, I want to know when the 2-year event, the 5-year event occurred. I want to be able to warn people and have my own warning system. So I'll talk a little bit more about that. But that also gets down into this bottom corner, which is a little bit harder to see, is this basically efficient port operations. We're in a global economy, and so you take someone like the Port of Portland in Portland, Oregon, and they have to compete with the Port of Seattle, Tacoma, Longview, Port of Long Beach, and many other ports along the West Coast. So if they want those large tanker ships to be able to come in, they can't keep dredging the Columbia River. So they have to be able to operate their facilities smartly. Water data availability. Never have enough data. Right? You collect a bunch of data, you learn anything, just I want more. And it just usually is not possible. It's oftentimes quite expensive to collect data. You have instrumentation costs, you have operation and maintenance costs, and then you have staffing expertise. Not every agency, not every private client can have field technicians on their staff to go out there and maintain equipment. Same comes to interpretation. Once you have all this data, what do you do with it? How do you interpret the data? How do you do quality assurance and quality control of that data? Sometimes if you're collecting the data as for regulatory compliance, it's mandatory. You have to check that data. You have to give some kind of quality rating to it. And again, that gets into data handling, it gets into staffing. The person who may be an expert at collecting the data in the field may not be an expert in interpreting regulatory requirements and how you stay in compliance. So again, these are all limitations really in many ways. And then the sustainability of it all. So sometimes the data you're collecting, it takes years before that data really becomes useful to you. I've worked on quite a few projects where the data has no longer available. You know, USGS keeps a lot of data available on the web, and it goes back to 1900 or older, but that's usually daily data. So if I want hourly or 15-minute data from 30 years ago, I have to make a request to have, in Portland, Oregon, to have someone in a warehouse in Tacoma, Washington, find the right box, pull out the files, and then send me hard copies. And those are usually graphs, which then I have to hire someone to digitize. So could it be better? Even better. But I don't blame them. It's the challenges of, you can't keep this stuff just around all the time. I've also had projects where I asked for drawings from the Corps of Engineers about what a particular facility looked like before they put it in, cross-sections of a river where they were going to put a dam. And they looked at the facility, their warehouse, the facility. They didn't have it there. They looked at their division office in Seattle, didn't have it there. So they told me it didn't exist, so we had to use best engineering judgment. So the model was reviewed, this was done 5 years ago, the model was reviewed and critiqued by the Corps of Engineers of USGS, and it held up to review. But the Corps said we weren't satisfied, so we're going to do it ourselves. And magically, 2 years later, they did the study, came up with the exact same results, but they included the drawings that existed pre-facility. I'm like, easy comment. Where there's a will, there's a way. So what is water modeling? Basically, it comes down to using computers to solve numerical equations for the physical processes of water. That could be the conservation of mass, momentum, considering density-driven flows, all those complexities of how water moves. And then, but you're doing this not just for the natural environment, you're doing this for the built environment. So this includes your closed pipes, your sewers, your water. It includes the plumbing in your house if need be. It also includes everything from estuaries, oceans, lakes. It includes lakes underneath glaciers. It's everything. If the laws of physics are the same, they should be able to be applied the same. So, but these common models that I've included here are hydrologic models, hydraulic models, water quality models, and sediment transport models. I'll talk a little bit more about each of those as I go on. But this is sort of the foundation. And these models are quite useful. So why model? Well, it's often used to help us solve problems. It's also used to help us fill in gaps. You can't collect data everywhere, and data is expensive. But if you collect data in enough places, a model can help you understand what's happening in between. And this is based on decades of understanding the physics. We use literature on how algae grows, how nutrients are taken up by microorganisms, etc. And that all goes into a computer model. And you have to then calibrate that model. Other uses include forecast future conditions. Maybe you're modeling flood scenarios, wanting to understand with a flood warning system, if it rains 3 inches an hour for the next half an hour, is that going to result in flooding and where along the system? So that can be done with forecasting over short periods of time. But really where it's used the most is assessing alternative designs or management scenarios. If we upsize this pipe, what happens? We know the city is going to grow like X, Y, and Z over the next 20 years. Where are we going to have weak points in our infrastructure? So models can help you do that. Ecosystem restoration is a big one. That's been mentioned a few times earlier today. And that's a big one. Trying out alternatives of if we restore this meander in the river, what does it do? Is it going to stay there? If we put large woody debris for salmon habitat in the river, is it going to stay? Very important stuff. I'm always fascinated in the restoration field how they're not held to the same standards as civil engineers are with sanitary pipes. The sanitary pipe is designed by a civil engineer to put in the ground, and it fails. Usually the engineer loses its license, the firm gets sued, the city gets compensation. If you design a restoration project and it gets blown out because of a bad design, no one gets sued. Urban infrastructure improvements is a big one. So to kind of go a little bit over these models, I won't belabor them too much. I'd rather show you cool stuff at the end. So basically, a hydrologic model is basically rainfall and runoff on the land. So it's understanding when you have water that's infiltrating into the ground, when it's evaporating off the land or transpired by plants, and then understanding when it percolates into the groundwater. So it's what we call the full hydrologic cycle. Oftentimes that then becomes the input to another type of model which focuses in river or in lake. So, and that's where the 1, 2, and 3-dimensional models come in. It's a way of breaking up a natural system or a man-made system into little tiny chunks you can understand. And obviously the more detail you want to go into as you go from a 1-dimensional, 2-dimensional, 3-dimensional, the more data intensive it is, the more effort it is to calibrate that model. Data needs. I thought I'd overwhelm you. I won't go over everything over here, but we've already talked today about GIS data, time series data, but also that includes facility operations. When do people open and close gates? And that's not just at a dam. That could be sanitary systems, overflow systems. All those type of infrastructure operations are integral to understanding how water moves. So this includes also the meteorology, so the weather conditions, air temperature, wind speed, direction, solar radiation. One of the big drivers out in the west is temperature streams. It's a big threat for salmon. And so if you don't understand what kind of weather conditions you have, you can't possibly model the water. Soil characteristics. Aerial photography has become a new thing. It's a new tool for calibrating flood models. There's only so many USGS gauges out there. They're fantastic, but they can't be everywhere. So literally looking at, in Oregon, for example, in 1996, there was a 100-year event. In some parts of the Oregon, it was a 500-year event. And people thought ahead and said, let's set up a bunch of planes. So people took tons of aerial photography. Those have become calibration data sets for models. But how do you store that and manage that format? And that's where we'll come to in a minute. So the more complex the problem, often the more complex the model, and the more data you need to support it. So oftentimes when someone comes to us with a problem, our first step is to understand that problem. And that may require more data to be collected or simply to review existing data. And then we then give them advice. You want to answer this question, you need this kind of model. You don't have enough data to do that kind of model. So sometimes it's a learning process for the client. But oftentimes these projects start off with simple data analysis, understanding the system we're potentially modeling. And then you have to build a model. And a lot of those data sets that were on the previous slide for what data needs are go into a model. And then you have to have another set of data that's in the system that becomes your calibration data. You have certain parameters in the model, but you have to be able to calibrate that model to ensure that that model is simulating reality accurately. And oftentimes, the longer the time series that you can study that over, the more trust you have in that model's ability to handle dry years, wet years, medium years, etc. And then lastly, the models then use as a tool to basically try out some of those management scenarios. What if we change the operations on these gates? What if we store more water in November and December? What does that do for us? This is a big incentive for folks to have that kind of work done. So where do we get the data? Again, we've talked about a lot of these agencies. One of the key things I found is that a lot of these agencies do a fantastic job collecting data, but I would say that a lot of these modeling type projects, sometimes up to 40% of the time of a project can be spent reviewing and analyzing data and understanding where it came from, the metadata behind it, and how to compare that and use that in potential modeling project. But we get it from a variety of sources. Sometimes a modeling study will even initiate new data collection. Oftentimes a model can guide someone in saying, this is your weak point in your system that you least understand, you should go collect more data. Data handling and storage, this is a big one. Since we receive the data from a variety of sources, and then we go ahead and apply that in a computer model that then helps a client to solve problems, we have to take responsibility for that data. So USGS is probably one of the top agencies in the world for being able to collect data and do quality assurance. But I've found errors with their data. And that's just simply statistics. They collect so much data, so many places, until someone digs into every little nook and cranny and they don't have the resources to do it. So it's definitely not a criticism. It's just a fact of how many sites they have, how much data they're collecting. And so you have to then justify any kind of correction you might make to that data to be able to defend that, potentially in court. So when we then have to take ownership of that data, we then, just as we take ownership of the model, we're handing that off to a client in the end. So once you start getting this data, GIS layers, LiDAR for topography, and then you start using that to generate spatial grids for a model. What do you do with that over the long term? We certainly store all our project files, but how long should we store them? When do they become obsolete? These are questions. It's not the base data It's what we've then adjusted in order to have a better understanding of the system or pulled together to use in a computer model. So I think this is a really important issue. Real-time control and management systems is another one. One of the things that we do as a company is we build management systems for folks, not just a computer model, but a data acquisition system with a computer model to then maybe give to hydropower operators. And so once you start doing that, you're now creating a database for the client that's going to store this data and model results on an ongoing basis. How do you handle that if you're just starting out? It's easy, but once you've been doing it for 20 years, then. And then simply delivery to the client. The client's objectives often are not the same as how you would build up a model. So they may want the data reported in a certain fashion, but that may be not the same as how you manipulated that data to prepare it for putting it into a model. And so sometimes there's a little bit of back and forth. And then ownership once it's in the client's hands. Once you pass that information on to the client, we don't have access to it. Well, we have our own version. We've had this happen in Florida, for example, where we built a model for a client, passed it out to the client. The client then hired another consultant to work with the model, and frankly, the consultant was left to the task. They didn't blame themselves. They blamed us. We looked at the model and in 20 minutes found out exactly what the problem was, fixed the model, and sent it back to the client. The client then fired that consultant. But that's pretty rare that it happens that quickly. But the idea is that once it's out of our hands, someone else can come along and say, "You did a bad job." So that's all I have. Do I have any more time? I do. Okay. So I just wanted to show you guys my animations will not work since we're working from. I'm just going to show you a couple examples of something that's pretty data intensive in the process. I'll show you what we're looking at. This is the Natchez River in Washington State. So the white is snow. So this is a rain on snow event. Any of you out far west know about these? I'm sure you do. So what you're looking at down here is there's a vertical line that shows you the current time. And this is what we call the hydrograph, so it's the flood event. And the depth of water. So the more red it gets, the deeper the water. And this is what we call it. The model uses a one-dimensional model and a two-dimensional model to computationally efficient code, meaning fast, and at the same time be as accurate as it can be. So what you're seeing is that as you're getting towards this peak, the floodplain is just massively increasing, deepening water, and then you're seeing it recede. We use gigabytes of data to develop a model, and we generate terabytes of output. So, would you put that on? Absolutely. I've got other cool ones I want to show you too, but this is one I really like. I want to explain this one too. This is a river in Bangladesh. And one of the things that we can do once we develop what we call a hydraulic model, which is simply the flow of water, is we can develop what we call a morphological model. So we're modeling the bed of the river. So not just sediment transport suspended in the water, but the actual bed. This takes a lot of data. The point is that the World Bank funded a project in Bangladesh to build a bridge over a large river. 3 years later, the bridge was sitting in the middle of a farm field. The river had moved. You want to talk about a lot of money, basically. So the purpose of this study was to understand what are the mechanisms that are going to move sediment in this river. In this particular river, it's a different river. And what you're going to see is right here in this area, you can see this is a rather deep part of the channel. And you're going to see it blow out. And it just gets bigger and deeper. It's a little bit fast, but you'll see a plug go right out. Now, to do something like this, just like doing water quality modeling, takes a lot of data. So not only do you have to have water level and flows, you have to have time series of cross sections of the river to make sure that the model is simulating the bed. You have to know what are the sediment size fractions in the river upstream and in the bed where you're building the model. So talk about complex. This one is a nice one for generating terabytes of data. And I'll just show you one more flood one. This particular one is in Alameda County area. So you're going to see it's a study where we looked at what's the impact of actually including the buildings in the flood. So we said, here's different flood events. The different colors represent 15-year, 50-year, 100-year, and 500-year events. And the upper panel is without building footprints. The lower panel is with the building footprints. And you'll see this bar moved to the right. And so it's kind of hard to see the nuances between the two in this kind of animation, but there are nuances where you see that if you're not including the building footprints, you're not having an accurate spatial representation of the flood. Let me tell you that a lot of FEMA's flood studies use a one-dimensional model. You couldn't do this with a one-dimensional model. And lastly, I'm going to show you the same river in Bangladesh that shows you a plan view. So one of the things that you can do is understand how a river grades over time. This is being used to do 30-year studies where you're saying, how does a river change? So you might calibrate your model for 10 years and then run it for another 30 years to see how a river might grade. So I'll show you this animation and then I'll call it quits. So this is basically the bed of a river changing, and you can see large paths, grades in the river that change over time. That was the 30-year simulation. Lots of data.